All right, good morning, everybody. Now, today's lecture, we're going to spend almost all of our time talking about the periodic table. We use the periodic table a lot in this class, and the textbook maybe gives you about 1 or 2 paragraphs on the periodic table. So I like giving a little bit more historical background of what really went into what this table is representing. And then you're going to start getting oriented with the periodic table this chapter. And then when we get into chapter 3 in quantum theory, you're going to learn a lot more about why the periodic table is organized the way that it is. Okay, but this is the modern periodic table that you have here in the lecture hall with a nice large print that you still can't read from your seats because it's a big hall. So you have various resources to access the periodic table. I want you to try to use the one that I've posted. Actually, I want you to use the one that I posted. It's there if you need extra copies. I usually have a couple of different versions of it or copies of it within the slides themselves, like especially and this lecture. I want you to start becoming familiar with these chemical symbols and what the names are. You don't need to memorize the numbers, okay? But I do want you to know the symbols and the names. And I want you to go up to element number 54. What is Xe? Who knows what Xe stands for? Xenon, xenon. I say xenon, you say xenon. Tomato, tomato, yeah. Okay? Now, it's not hard, all right? A lot of these you're already very familiar with. Some of them you may not be, okay? So make yourself a stack of flashcards, okay? And just practice it over and over again. And it's the ones that you aren't familiar with, those are the ones you really need to learn. And then, you know, a couple times through it, and you'll know what they are. And it's important to know what these symbols are and their names are, because then when you see different compounds in the class, and it doesn't necessarily say what the name is, you'll be able to interpret it, and vice versa. But I do try to use the same ones over and over again to help reinforce the chemistry that we're learning. It's not so much just memorizing this stuff, but this is a chemistry class. So yeah, I do expect you to know these, right? At least up to 54. So there you go. Back when scientists first started trying to organize these elements into some kind of a system that they can make predictions on, they didn't have 118 elements that we have listed on our modern periodic table. They only knew about 60 elements at the time. And by the way, this was back in the 1860s. Not that I would ever test you on a date, okay, but this is just for historical perspective. And there were lots of scientists that were trying to understand how these 60 elements might be organized in nature. Are there properties that we can recognize that are similar or different? Are there trends that we can see and put this into some kind of an order where we can make some important predictions? And Mendeleev and Meyer, these are the two of particular note who usually get credit for this, because they weren't the only ones that were doing this, okay? But they made some significant contributions to this science that really paid off in the end. And so they get recognized for their work. But what was the work? What were they doing? What were they able to do back in the 1860s? Right? Not much compared to what we can do today, all right? But they did know a lot of things. But let me tell you what they didn't know. They didn't know about protons and neutrons and electrons. Because if you go back to the dates of those experiments we talked about last class, that was after this stuff, all right? So when Mendeleev and his friends were trying to understand what's going on, they didn't know about protons and neutrons and electrons. They're still working with Dalton's model, that atoms are just these blobs of stuff that don't have anything inside of them. But if you divide them, they no longer are that element. Okay, so there's still, oh, and of course that they combine in small whole number ratios. Remember, that theory was around for close to 100 years before Thomson's experiment found evidence for an electron. Okay, so what did they know? They knew a lot, actually. So they could measure the atomic mass. That's the overall mass. It's not the number of protons and neutrons, okay? And they can measure and then look at ratios. And when they look at ratios, they did have something of advantage there, which was Avogadro's law, which is something that we'll study at the end of this semester with the gas laws. But simply stated, Avogadro's law said that their equal volume of gases have the same number of particles, all right? So if they can measure the mass of, say, one volume of oxygen and the same volume of hydrogen, they can get a ratio, they can get a mass ratio of that. So oxygen to hydrogen, the same volume of that, following Avogadro's law, they have the same number of particles. So by mass, they can then find that oxygen is about 16 times more massive than hydrogen is. There's a 16-to-1 ratio there, following that principle. Now, if you look on the periodic table, you can't see it probably from your seats, but oxygen over there has a mass of about 16. I'm not going to put units on it right now. It's atomic mass units. 16, and hydrogen has a mass of about 1 on our modern periodic table. That's your 16-to-1 ratio. They can do this not just with oxygen and hydrogen, but lots of the other gases at the time and other materials as well. So they can measure those ratios. And from those ratios, they could order them based on mass. So ratios gives you order by total mass. Okay? They could also observe lots of physical properties and chemical properties. And by now, I would hope you know the difference between a physical property and a chemical property. Some of the physical properties they were looking at, here are some that you haven't heard of before, perhaps, like whether something was malleable or ductile. Ductile. Malleable is something that you can mold easily into shapes without it breaking, like, you know, silver and gold is very malleable. You can bend it into jewelry and it doesn't break. So you can compress. So malleable is something that you can compress or deform. Ductile, anyone know what ductile means? I should have asked for malleable too. Sorry, you raised your hand? You can stretch it out into a thin wire without it breaking, okay? Yeah, that's ductile. So stretch into thin wire. Like, you know, copper. Copper is very ductile, right? These are things that they can measure at the time. Of course, there's lots of other physical properties that they can look at that you're more familiar with, like whether something is shiny or whether something is brittle. Let's spell brittle properly. They can measure the melting points and the boiling points. Those are all physical properties, right? Melting point and boiling points. They can measure the density. All sorts of physical properties. And then there's chemical properties. Yes, question. Freezing point, yes, there's plenty more, right? Anything that you've learned that's a physical property, if they could have measured it back in the 1860s, they would have, okay? But then there's chemical properties. Chemical properties are things that when you measure them, you're measuring the reactivity of something. The act of measuring it means that it's changing into something else. It's undergoing a chemical reaction. So a chemical property. And lots of things like when you mix it with water, it's very violent. That's also a chemical property. There's other chemical properties, like, for example, when you mix carbon, C for carbon, with hydrogen, you'll find that carbon combines with 4 parts hydrogen. Now, many of you may remember, if you took chemistry recently, that carbon can form up to 4 bonds with things, okay? Or oxygen can form up to 2 bonds with things. That's what we say now. But back in Mendeleev's time, they were talking about the combining power. When you mix carbon and hydrogen, you find that it has a combining power of 1 to 4. When you mix it with oxygen and hydrogen, what do you suppose the combining power of oxygen is? 1 to 2, like H2O, 2 hydrogens for every oxygen. These are things that they were able to measure back then. Reactivity with other materials, like I mentioned, mixing with water, it's very, very violent, right? For example, when they mixed Li, what does Li stand for? Lithium, that's right. Or Na, what does Na stand for? Sodium. Or how about K? Potassium, all right? You mix those 3. Now, where are they on our periodic table? They're over there on the left-hand side, stacked up on the first column, all right? But scientists realized that when you mix those with water, they reacted very violently. And pretty much it looked the same. The reaction, the violence of that reaction looked very, very similar, okay? But these have very different atomic weights. Or masses. These have different atomic masses. Whereas there's other trends that they can observe, like, for example, here, maybe you don't know these. What's OS? It's osmium. Very good. This is beyond xenon, by the way, so I'll write them down for you. Osmium. How about IR? It's not iron. Good guess. It's iridium. And PT. Maybe you guys know PT. There's lots that start with P. Yeah. It's platinum. Very good. 10 points to Gryffindor. All right. Now, these 3, you may find, you're searching around on the periodic table, where are they? All right. You'll find them kind of in the middle. They're a little bit lower down. Okay. OS, IR, and PT. They're grouped together. So they have, as you'll be learning, they have very, very similar atomic masses. And they also have very similar properties. So you can see that this is starting to get a little complicated. It's not a simple thing. If it was simple, they wouldn't have their names associated with this, because everyone would have realized this. There's lots of trends for them to try to analyze to see from these 60 elements, can they come up with some kind of a comprehensive system that explains the observations? This is the scientific method that we went over the second lecture, right? Come up with a hypothesis and a model that explains your observations and allows you to make good predictions on things that maybe haven't been discovered yet. And that is why Mendeleev wins the prize here. Mendeleev not only explained the observations, what he did that the others didn't was he put in placeholders with clear predictions for elements that have not yet been discovered. But by making those predictions, Mendeleev was actually able to help future scientists make these predictions, because Mendeleev made predictions on, well, I don't know what this element is yet, but it should, when you find it, it should have a density of this. and a melting point of that. And it should be shiny or it should be brittle, right? And in the next 10 to 20 years, actually, many of these elements have been discovered, aided by Mendeleev's predictions. But the point of my story here is that Mendeleev has an element named after him, Mendelevium, all right, number 101. You'll find that there's lots of elements here named after important scientists. Here's ES. Who do you suppose ES is named after? Einstein, Einsteinium. Maybe it's not just people, all right, but there's also places. Oh, here's one. How about RF? Who do you suppose RF is named after? Oh, stop yelling it out. Someone else who didn't hear what she said. It is Rutherfordium. So Ernest Rutherford, who we talked about the last time, all right, gets an element named after himself. And, you know, I like pointing these things out from time to time. Sometimes it's not a person, but it's a place. Now, one thing you might notice on our periodic table here hanging in the hallway, all right, number 117. Where is it here? Number 117. There's still placeholders. Even 10 or 20 years ago, we still had Mendeleev's placeholders on our periodic table. Because when you look in the hallway, it says UUS. Now, I bet nobody knows what UUS stands for. It's Latin, and it stands for unobseptium. I had to look it up, all right? It's element that has yet to be discovered that has an atomic mass of, or an atomic number in this case of 117, unobseptium. The one that's 117 that hasn't been discovered yet. But now it has a symbol on it, TS. Anyone know what TS stands for? It's not titanium, it's Tennesseeine. It's not Tennesseeum. It's Tennesseeine. Because some of the research that led to its discovery was done at Oak Ridge National Laboratories. So there you go, all right? Now we have scientific evidence for 118 elements. So every placeholder on this banner that was put in here when this building was built 10 years ago now has been replaced with an element that has some scientific evidence to support its existence. Yeah, so it's not Tennesseeum, it's Tennesseeine. And one reason for that is because it's placed in the periodic table with all of these other elements here: fluorine, chlorine, bromine, iodine. They all end in INE. Okay, as you go down, now the banner here in the hallway is green, okay? And as we'll discuss in a moment, these are grouped based on their similarities. This is a group called the halogens. I'll spell it out for you in a little bit. They all have similar properties. And so when Tennesseeine was this evidence for, when it was named, it's following the naming convention in this case. Okay, how did Mendeleev sort things out? Because Mendeleev's actual periodic system looks a little different than our modern one. There's a version of this in the textbook that is very confusing. I don't recommend you try to understand that. I pulled this one off online. This is from Mendeleev's original publication. Now, yes, he's Russian, but at the time, German was the language of science. And so this is in German, if you know how to read German. And here you can recognize a lot of these symbols, okay? But instead of organizing things in columns, Mendeleev organized things in rows. So I just pointed out those halogens, fluorine and chlorine and bromine. So here they are in Mendeleev's system: F, Cl, Br, and then J. Now you might think, well, what's J? There's no J on our periodic table. But let's just say J is what we now call iodine. And I want to point out something else that Mendeleev did that I haven't talked about yet. And that is the columns here, they're organizing it by mass. Remember, they can measure the overall mass, even though they didn't know about protons and neutrons, okay? So going down each column here, we're increasing by total mass. because it would make sense. Oh, this one's heavier than this one, so this one comes next, right? And if you go down all of these rows, sorry, all of these columns, you'll see that trend until we get to J. So what's right above J there? Te, tellurium, okay? Tellurium has a mass of 128, and iodine, J, has a mass of 127. That comes from their measurements back in 1860, okay? Everything else here, though, is ordered by its increasing mass, but Mendeleev puts tellurium first and then iodine. And he recognizes that this is out of order, and I'm putting these out of order. That's why there's a question mark here. I'm putting these out of order because I think it's more important that iodine be aligned with bromine, chlorine, and fluorine because it shares the chemical and physical properties. That's more important than just ordering this by mass. And if I order it by mass, then that part doesn't make sense. And maybe there's something else going on that we just haven't discovered yet. Right? Here's a hint: protons and neutrons. Okay, they didn't know about those. So Mendeleev was smart enough to recognize that maybe something else is going on. I'm going to put these out of order, but I'm going to highlight that. Now, if you look at our modern periodic table, here's tellurium and iodine. And look at the total masses here: 127.6 and 126.9. They're still out of order. Mendeleev was right. We'll explore why this is in a little bit, okay? But I'm just pointing out that even that trend still exists even in our modern periodic table. Now, of course, the other contribution that Mendeleev had were these placeholders that I already told you about. And there's lots of examples, like these question marks here. These are all placeholders. Here's aluminum, here's silicon, and then there's something that should follow it that hasn't been discovered yet. But when you do discover it, it should have that predicted density and that predicted melting point and so on and so forth. And there's even some examples where scientists found these new elements and maybe there was a discrepancy and there was a little controversy. But through the scientific method, right, you don't just do it in one laboratory, you publish your results. Other people try to repeat your results, so on and so forth. So if there were any discrepancies, that was taken care of through the scientific method. After all of that, Mendeleev's predictions were always confirmed. And so he gets the recognition for being the so-called inventor of the periodic system, but it really wasn't just Mendeleev. So that's just a little bit of historical insight. You won't see this in the textbook. What you will find in the textbook is the modern periodic table. This one's color-coded, so I stole this from another source. Now, one major difference, though, remember, Mendeleev, they only had total mass. Our modern periodic table, it's organized by the atomic number. Now, what's the atomic number? That's the number of what? Protons. All right, protons are pretty important. I mean, it's all important. And if you notice, here I don't need to flip back. Here's tellurium and iodine again. And I already pointed out to you how they're out of order with the total mass, but they are in order by the number on top, the 52 and the 53. That's the number of protons. That's the atomic number. The number of protons. So everything on our modern periodic table is in order of the number of protons, the atomic number. And that's one very important distinction because that's something that Mendeleev didn't know back in 1860. All right, so let's make some sense of these colors. There's two main categories of elements that we might describe. Most of them are what we call metals. Now, this is probably stuff I could have put in the introductory video because I think everybody knows this stuff. So everything here in blue is the metals. Can you all see that? Everything over here in yellow are the non-metals. And then this little staircase here in green is a special category of elements that have characteristics that are in between metals and non-metals. So we creatively call these the metalloids. So some basic characteristics, just some general characteristics of metals. Let me get that down a little bit. These tend to be materials that can conduct heat and electricity. These tend to be materials that are malleable and ductile. These tend to be shiny. I'm sorry? Are these physical? Are they? Is malleability and ductility, are those physical properties or chemical properties? They're physical properties, all right? It's something that you can measure, and in the process of measuring it, you're not changing the identity of the thing that you're measuring. Same is true for conducting heat or conducting electricity, right? If you're conducting electricity, a copper wire conducts electricity. Once you've run electricity through it, is it still copper? Yeah, so that's a physical property. All right, they tend to be shiny, and they tend to be solids at room temperature. RT is room temperature. I guess I should spell that out the first time. Room temperature. Here, I want to spell out temperature. I think you know what that is. And again, these are all tends to be. These aren't absolutes, okay? Whereas the non-metals are pretty much the opposite of that. Non-metals are mostly gases at room temperature. Not all of them. In fact, the ones that aren't gases, they tend to be brittle, or they tend to be liquids. But in general, most of the nonmetals are gases. Most of the metals have those properties. And then, of course, we have the metalloids, which really doesn't have much of a definition. It's just in between those two. All right, now these are sorry, this is called the periodic table. So all of these observations, they have a periodicity to them. That's how they're organized in this way. So you can see it's written down here, the periods now, these are going to be the rows. And the columns are the families or groups. And some of them have names. And it's good to be familiar with these names because they're used a lot, and you should know what they mean. So for example, the family name in group 1, so everything that's in this first column here These are called the alkali metals. Everything in group 2, these are called the alkaline earth metals. We don't have a family name for every group, and we don't name the groups in the middle. I'll talk about those in a minute. So if we go over to the right-hand side, the far right, I think probably most everybody knows what this group is on the very far right. These are the noble gases, or sometimes they're called the inert gases. I already named this group for you, the ones that have fluorine and chlorine and bromine and iodine. These are the halogens. And there's another group named down here that you don't hear too often, but the textbook talks about it. These are the chalcogens. That name comes from the fact that those elements are often found in materials with copper. So that's where chalco comes from. And then you see that this isn't just a box. This is a very oddly shaped box. The more overriding question is, why is the overall shape so funky looking? Okay. Now, to answer that question, we're going to hold that off to chapter 3 for sure. But I'll just tell you that this is organized based on quantum theory. And we're not going to study that until chapter 3. So once we do that, you'll have a much better idea or understanding why it is shaped the way that this is. But a few more names for you to know right now, as we're taking our survey here, is we do have some parts that are taller than others. So these tall columns, the first 2 on the left, and then the last 6 there on the right, okay? These are what's called the representative elements, or also called the main group elements. I usually call them the main group elements. And you'll notice that at the top of each column, we have numbers and Roman numerals. And there's 2 systems. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 18. And then we have Roman numerals followed by the letter A or the letter B. Unfortunately, scientists haven't agreed upon which system to use. So some periodic tables show both of them. But the A refers to whether it's a main group element or whether it's not a main group element. So if it's not a main group, those in the middle, these are the transition elements. And these are all metals, okay? So every element that's a transition element is also a metal. So we often also call these the transition metals. Those have Roman numerals followed by a B. And you may notice there the system is even more complicated. Like look in the middle for columns 8, 9, and 10. Those are all listed as Roman numeral 8B. But take a look at some of those pairings. Well, I wrote over one of them because I already told you about this one. Looky down here. Osmium, iridium, and platinum. Remember when I told you about those guys, right? They have similar masses and similar properties. You'll find those on Mendeleev's 1860s periodic system, okay? They all had about the same chemical and physical properties, so they were kind of considered in the same group. And so for more historical purposes, the Roman numeral 8B comprises all 3 of those. Yes, question? Is the purple that, so it's just a clarification question. Everything that's a shade of blue or purple is considered a metal. The reason they're colored differently here is they're just separating between the main group elements and the transition elements. And then even down below, although you might not tell, that's another shade of blue. Because what's down below here is what's called the inner transition elements. And there's nothing fancy about this. It's just to save space. You notice that they come in. If you follow the numbering, remember, these are all ordered by increasing number of protons, increasing atomic number. So we go from barium to lanthanum, 56, 57, and then we get to 58 down here, 59, and we'll go all the way to 71 before we come back up here to 72 hafnium. And it's just a way to save space, okay? Just like we've got the transition elements inserted in the middle of the main group elements, we could have displayed this even wider with the inner transition elements inserted in between those transition elements when we got to row 6 and row 7. Okay. We won't be working much with the inner transition elements in this class, but it's just a way to kind of orient you around the periodic table. Okay, so in general, though, if we want information out of an element and we want to read it from the periodic table, all right, they all kind of look like this. So I'm going to draw a box. And here's what it would look like for carbon. You'll have the element symbol. And by the way, the element symbols, they're always capital letters. And they're either one letter or they're two letters. If it's one letter, it's always a capital letter. If it's a two-letter symbol, the first is capital and the second letter is lowercase. It may sound silly for me to emphasize that, but this is how the symbology works. It is incorrect if you have a two-letter symbol and you don't have the first one as a capital letter and the second one as lowercase. And oftentimes it's not correct because it could mean something else that we do in science, some other symbol that we use. So on the top is going to be the atomic number. There's 6 protons in carbon. Now, some periodic tables actually list the name, not all of them. The one I'm having you use doesn't have the names because I want you to know the name. But if the name is listed, it'll be listed underneath the symbol there. And then down below, we have another number that we're going to talk about next lecture. That's going to be the atomic mass. That's what Mendeleev and his friends were able to look at. All right. This number down here is the atomic mass. All right. That's next lecture. This number up here is the atomic number. Oh, it's right. I don't need to write it again. It's right here, the atomic number. All right, so atomic mass, we'll do this next lecture to understand what's going on there. Any more questions about the organization of this before I move on? Lots of good questions. I don't want to stop you from asking questions, but some questions are just better answered once we get just a little further along in the class. All right, so ions are something else that we put in our little memory chant at the beginning, right? If we change the number of protons, what do we get? You change the number of protons, what do you get? A different element. If you change the number of neutrons, what do you get? A different isotope. We'll talk about that on Monday. And if you change the number of electrons, you get ions. And that's what we're going to talk about briefly right now. But really, we're going to be talking more in depth about ions in future chapters, chapter 3 and chapter 4 and so on, okay? But let me introduce you a little bit more to that concept now. When things gain or lose, this is losses, when things gain or lose electrons relative to the number of protons, okay? Because remember, if we're talking about ions of the same element, the number of protons stays the same. And the protons have the positive charge and the electrons have the negative charge, okay? So when something loses an electron, and I'm just gonna symbolize an electron with a lowercase e with a negative sign on it. When you lose electrons, but the protons stay the same, overall, you're going to have a positive charge, right? Because you have fewer electrons than you have protons. And the protons have the positive charge, the electrons have the negative charge. So when you have an overall positively charged ion, we call that a cation. That's how you pronounce this word, cations. When you gain electrons, you end up having more negative charge than you have positive charge. So you end up with a negatively charged anion, and that's what we call negatively charged ion, and that's what we call an anion. And you can see some of them are listed for you here, overlaid on their position in the periodic table. And you'll notice a couple things right off the bat. Well, actually, why don't I ask you, what do you notice right off the bat in this? Say louder. What about hydrogen? Right, but what kind of trend do you see? Do you see any organization of this? Yes. It goes from positive to negative. Right, so one side has all the negatives and one side, most of it has all the positives, right? So what kinds of classification of element would form a positively charged cation? The metals. See that? These are all the metals. Now the color coding has changed a little bit. Right? And the non-metals, all right, those tend to form negatively charged anions. Okay, so here's another trend. All right, metals tend to form cations, and non-metals tend to form the anions. Here's one example, all right, of a metal. Let's pick on sodium. Sodium is a metal, and sodium can form a positively charged cation. And when it does so, we would write it this way, right? The chemical symbol Na, we're not going to put in the atomic number and the mass number like I showed you at the beginning, but I am going to put the charge. The charge goes in the upper right-hand corner. Sodium, when it forms a cation, forms a 1+ cation. Right, and for the anion, I'll pick on chlorine. When chlorine forms an anion, it forms what we call the chloride anion with a 1- charge. Now, don't worry about the names. We'll cover how we name these things, going from chlorine to chloride, when we get there in chapter 4. Okay, chlorine is a non-metal. It forms an anion, and when it does so, it picks up a 1- charge. And we all know what happens when you mix sodium ions and chloride ions. What do you get? You get sodium chloride. Okay, NaCl, table salt. In fact, don't try this at home. Go to YouTube, because when you mix chlorine gas and sodium, you get this reaction happening, and it's quite explosive. All right, so don't try that at home. This forms an ionic bond. These are ions, okay? And so the bond that's formed here is an ionic bond, something that we'll cover in greater detail when we get there in chapter 4. Okay, but there's another trend in here, not just who's positive and who's negative. Take a look at the main group elements here. Does anyone see another trend in the main group elements in how they form ions? Let me see if somebody else has. Yes. The charge is associated with the group. Very good. Everything that's in group 1, when it forms an ion, it has a 1+ charge. Everything that's in group 2, when it forms an ion, it forms a 2+ charge. When everything's in group 17, now this one's a little trickier. When everything's in group 17, it forms a 1- charge. When everything's in group 16, it forms a 2- charge. All right, and everything in group 15 is a 3- charge. Now, when we start getting more into quantum theory and even beyond that, and you start learning things like called the octet rule that maybe some of you have heard of before, you'll start to understand a little bit better about why this is the case. But right now, we're just identifying trends. If you're looking at the main group elements, and you can just look at the periodic table for the main group elements, you can predict how many electrons are going to be gained or lost and what the ion charge is going to be. That's a very regular pattern, okay? So you can predict the ions formed here for the main group elements. Now for the transition metals, it's a little bit different. Transition metals, they all form ions, okay? But you can't predict what the charges are going to be. Now, when we get there, I might show you a couple of examples of how we can explain why, for example, Fe, what does Fe stand for? Iron. Everybody knows Fe is iron, right? Iron can form a +2 cation and a +3 cation. And when we get there, after quantum theory, I'll give you a little bit of insight as to how that may happen, okay? But in general, you can't just look at say, let's see, Cu. What does Cu stand for? Copper. You can't necessarily look at copper and know that it's going to form a 1+ or a 2+. Right? So lots of these things you just have to know. And I'll give you some insight for them as well. All right? But the point here, because we're talking about the periodic table, is even ion formation also follows this periodicity trend. Okay? So when we come back on Monday, we're going to explore why it is that tellurium and iodine are in a different order. There's another case of this too. When we get to, let's see, where is it? Cobalt and nickel. Also have the same out of order. See, the mass of cobalt, CO, is a little bit greater than the mass of nickel. Okay, we're going to start to explore that next time. It has to do with isotopes. So we're going to be doing some math next time. Before you pack up and go, let me just